IFIMAC-ICMM seminar series on condensed matter. I'm Laura Riaga from Universidad Autónoma of Madrid, and I will be the chair of this session. So let me remind you quickly how to proceed. We will have time for questions after the seminar. You can use the raise hand button to let me know that you have a question, but you will be able to unmute yourself and ask directly to our speaker. So it is my great pleasure to introduce today to our invited speaker, Alberto Fernandez-Nieves, who is an experimental soft matter researcher. Alberto did his PhD in his hometown in Granada, and later joined as a postdoc the group of Professor David Waits at Harvard University. Later, he got his assistant professorship at Georgia Tech, and that was in 2008. And later in 2014, he got promoted to, he got his tenure and got promoted to associate professor. And very recently, he came back to Spain, so we can have him here. And he joined as an ICRIA research professor, the University of Barcelona, where his lab is currently located. Alberto has made significant contributions to the soft matter field. To tell some of them, he has contributed to the physics of geometrically frustrated liquid crystals, to surface tension instabilities, and to the thermodynamic of colloidal gels. So it's really a great pleasure to have Alberto here today. And he's going to talk today about toroids, active nematics, and topological defects. So I leave you with him. Alberto, the screen is all yours.
Perfect. So thank you very much. It's a pleasure to be able to tell you a little bit about some of the work that we've been doing in my group for the past few years. So mostly of what I'm going to tell you, it's work done by a former grad student, Perry Ellis, who's terrific. Recently, Gio Nambisan, another grad student in the group, and Alexis De La Cota postdoc, they are continuing some of the work that I want to tell you about. Winnie was involved in the early stages of the project, and I'll also briefly discuss some of the work of our theoretical collaborators, Dan Pierce and Luca Giomi. So I'll briefly mention some of the numerical and simulation results that they have contributed. Okay, so of course you're all familiar with the fact that drops are spherical, right? This, as you know, it's due to surface tension, right? And the sphere, it's the preferred shapes. It's you can refer to it as a minimal surface shape, right? You minimize the area for a given volume, and because of that, having non-spherical shapes, right? It's an unstable instance, and being toroidal, right? It's not an exception. Yet we've become over the years incredibly interested in tori, and the single simplifying reason of why it's because it's a very simple, or relatively simple mathematical surface. Yet it is curved, and it's interesting. It has interesting mathematical properties. So I'm going to give you three of those more specific reasons of why the tori appeal to us. Okay, so the first one pertains to what we call Gaussian curvature, which can be defined as the product of the two principal curvatures at a point on the surface. And if you consider the torus, it is a surface with non-constant Gaussian curvature. It has regions in the outside that are elliptical, right, spherical-like, with positive Gaussian curvature. It has regions in the inside that are hyperbolic, right? They're saddle regions, right? Those have a negative Gaussian curvature. And then it has two lines that are locally flat, right, with zero Gaussian curvature. And of course, this right away, you recognize that it's very different from the sphere, which is a constant curvature surface, right? With a constant Gaussian curvature equals to 1 over the radius of the sphere squared. The other reason pertains to a different type of curvature that we call mean curvature. Okay, this is simply the average of the two principal curvatures at a point on the surface. And like Gaussian curvature, mean curvature also changes from point to point. And that, again, is very different from the sphere, right? Which, as you know, it's a constant mean curvature surface, and we value 1 over the radius. The third reason we find tori appealing, it's topological. right, is that if you take this geometric object that I've told you about, the Gaussian curvature, is an intrinsic property of the surface, but it informs about the local shape of your surface, and you integrate it through the whole surface, you get an object, right, that doesn't depend on the geometry. Okay, that we refer to as a topological invariant. It's called the Euler characteristic of the surface, which we can relate with the number of handles, or more properly, the genus of the surface. Okay, so the torus has a handle. That's why we say it is topologically similar or equivalent, right, to a cup of coffee, right? You can continuously deform one into the other, right? And that implies it has another characteristic of 0, and that makes it topologically distinct, right? Globally very different, right, from the sphere, which, as you know, has no handles and another characteristic of 2. Okay, now from my point of view is that these simple yet interesting mathematical properties, they have interesting physical consequences, right? So they yield to interesting physics phenomena that we've been attracted to over the past few years. Okay, so I won't focus today on some of the fluid mechanics aspects, right, and some of the many interesting instabilities that you can see when you deal with toroidal drops, right? So this, if you're interested, I can tell you at the end of the talk a little bit more, or you can send me an email. But the other interesting consequences, it's the focus of today's talk, and it's more in the realm of condensed matter. Okay, since these interesting mathematical properties bring what I find a fascinating interplay between order, topology, and geometry. Okay, so this interplay will result in many instances in ground states that are populated with defects. And even if there are no defects, right, the ordered material, when confined within a torus, right, may adopt an intricate arrangement, right, and a very remarkable overall organization of the ordered material. Okay, so what I'm going to tell you briefly, because we've been doing this already for quite a number of years, right, is how we make and how we stabilize toroidal droplets. Okay, and then I'll move on to the bulk of the talk. So I'll tell you about looking at a nematic liquid crystal on top of a toroidal surface, right, on a toroidal surface, right, but with a little bit of added ingredient, which is that the nematic is going to be out of equilibrium, and it's going to be what we call active. Okay, so I'll briefly try to highlight why we're interested in this, what got us into this problem, and they'll then pay attention to some technicalities, right, that we're very proud of. Right, so I'll spend some time telling you a little bit some of these technical details, and then I'll try to show you that we've seen experimentally a coupling between the type of topological defect that may be populating the surface and the underlying Gaussian curvature. Okay, so I'm going to tell you about what's referred to as curvature-induced defect unbinding, but there will be a little bit of subtleties here because this is an equilibrium prediction, right? And as I told you already, the system we're going to be working with, it's out of equilibrium, it's active. And then I'll tell you about some surprises in the results, right, which pertain to how the defects distribute on the torus. And then I'll finalize and tell you a little bit about some of the work that we're currently working. Okay, so how do we make toroidal drops? And then for this, let me take a few years back, right? And so I'll tell you a little bit about history, right? At least my history, which was to look at drop formation in what we refer to as co-flow, okay? In an experimental setup that Laura is very familiar with, right? It's capillary microfluidics. Okay, so the setup is conceptually very simple. So you have glass pipes that are relatively small, right? So what we do is that we use a capillary with a square cross-section, right? Typical inner side is about 1 millimeter. And then we have a cylindrical capillary. Now we've pulled to have a tip, right? That has a size which is about 10 microns. And then what we do is that we fit the inner side of the square cross-section to the outer diameter of the circular cross-section of the cylindrical capillary. We put one inside the other one, and then the tip is nearly at the center of the square. And then what you do is that you pump a liquid through the cylindrical capillary, and then through the voids left between the cross-sections, right, we pump what we refer to as a co-flowing liquid, okay? And when you do that, you can see something that you typically see in the faucet if you're careful and you have a small flow rate, which is dripping at the nozzle, dripping at the tip, okay? So here, there's no gravitational effects as in the faucet in our kitchen, right? But it's all about drag. So when the drop grows in size, the drag increases and eventually overcomes surface tension forces and causes detachment and formation of one drop at a time. Now, if you bring the speed of the outer co-flowing liquid, right, the one that's co-flowing with the inner liquid, so you crank up its speed such that this dimensionless group, the capillary number, that balances the importance of viscous and surface tension forces, its order 1, you can transition from dripping to a different regime. This regime you can also see in the faucet if you, again, gently crank up the flow rate, right? You induce formation of a jet. Okay, the jet thins a bit as you move downstream, and then you get break up into drops. And this is, of course, due to Rayleigh plateau. It's a surface tension driven instability. Okay, so how do we make toroids? So we use this knowledge, right? And what we do is that we have a continuous phase, right? This is going to be our co-flowing liquid. And then we bring a needle below the free surface, right? And we inject the inner liquid, okay? And you do that such that the capillary number of the outer fluid is larger than 1. So you're going to jet at the needle. And then you also have to be quick, right? Because if you're not too quick, right, then the jet will break. The other thing is that the continuous phase is rotating. In this case, it's viscous flow. So the jet follows the streamlines, right? And it beautifully closes into a toroid. Again, you, in addition of having a capillary number of the outer rotating fluid larger than 1, you need to have a period of rotation which is sufficiently small compared to the breakup time of the jet that you're making. So very simple. Yet despite its simplicity, you can beautifully control the geometry, right? You can control independently, right, the radius of the central circle, because you can shift the needle and move it a certain distance away from the rotation axis. And then you can also control the tube radius, right, by infusing more or less volume. So it's simple, but you can do lots of things if you're interested in tori, right? Which we were. Okay, so what happens when you've made it? And these are some of the very early results, right, in the lab. So this is a side view of a torus, right? So the torus is coming out of the screen, right? So one of the things that you see is that once you've made it, you watch it evolve, and of course it's going to break. Okay, and this is Rayleigh plateau breakup, reminiscent of how a jet breaks. Okay, you're pinching at one point, conservation of volume causes the other cross section to grow, and eventually you become a sphere. Okay, but then since this is Rayleigh plateau, of course, if you have a torus that's sufficiently thick or fat, right, such that the inner perimeter it's tiny, right, then you cannot grow an unstable mode of the Rayleigh plateau type, right, and then something else has to happen, right, because you're still a tori and you want to eventually become a sphere. And what happens is that it's a distinct mechanism in which the hole, right, shrinks in time. Okay, and that's a distinct way in which your tori becomes a sphere. Either of them are driven by surface tension, which is the key player. So if you want to stabilize a toroidal drop, you need to beat surface tension, right? That's the key. And we tried charging the tori, and we saw some interesting fluid mechanics there, but we weren't unable to stabilize the tori. The way we were successful in doing this was when we decided to replace the outer fluid, the rotating fluid, which in the movies that I've shown you, it's a simple liquid, right? For example, oil, right? So we replace that with what we refer to as a yield stress material. Okay, so this is actually a solid. It's an elastic solid, right? But then once you apply a relatively small stress above what we call the yield stress, you can fluidize the material and it behaves viscous-like. Okay, so the yield stress material we use, it's a granular solution of swollen hydrogel. So you have these particles that are granular in size, right? They're not colloids, they're larger, so they don't exhibit thermal motion, right? And they're swollen. That's why you can clearly see that it is pretty transparent. And then you bring it to a density when you jump, okay? And then you have something that's a solid. You can clearly see it. Look at the free surface, right? It is not flowing. It is bumpy. So it's a very soft but weak elastic solid. Okay, and then what you can do is that you can generate your tori as before, because when you're making it, the stresses are above the yield stress, so you are fluidizing the yield stress material, hence you can make your tori, right? This is an example of one of the first ones that we made where we were successful, right? And but then what happens now is that the shape remains stable. You can even deform the torus, and the deformation is retained as a result of the elasticity. Right? You can poke on it. Okay, so this is a toroidal droplet. Right? It is not a torus, as you see, but it's toroidal. It has one handle, right? And it's unstable in time. The physics of this, right, despite its complexity, it's the balance between the relevant players, right? So you want to be surface tension, right? And you have a yield stress that's competing with it, the elasticity. So of course you think of the units, you need a length scale. So that defines a critical length below which surface tension will cause the torus to either break or shrink, and above which you're successful in stabilizing the toroidal shape. And these actually, we now have 2 patents on this, because you can think of this as a way of drawing. So it's kind of a new way to 3D print, or it was a way to 3D print. Okay, so that's done. So let me continue and get into the meat of the talk. Okay, so we're going to be dealing with nematic liquid crystals, right? So nematics, you break the continuous rotational symmetry of the isotropic vase, right? So this typically happens when you have, or this can happen when you have anisotropic objects, right? Such as rod-like molecules, right? Elongated molecules or colloids, right? And then a sufficiently low temperature or high density, you have this phase transition onto the nematic phase, you develop orientational order. There's no positional order, just orientational order, right? Which you characterize because of the up-down symmetry with what we call the director N. Okay, but then since you've broken a continuous symmetry, of course, you need to have rigidity to retain the order. So what that tells you right away is that nematics, even though weak, right, they're elastic materials and they feel distortions. Okay, and typical ways to distort the nematic are ways to deform the director field, right? And you can twist, bend, or splay. All right. Now, if you consider a nematic of the type that I've told you, right, a material with that type of orientational order, and you put it on a sphere, right, the nematic has to fulfill what's called the Poincaré-Hopf index theorem. Okay, so this is an important mathematical theorem that tells you that the index of the field, right, has to be equal to this topological invariant of the surface, the other characteristic. Okay, the index of the field is nothing but the sum of the topological charges associated to the singularities in the director field. Okay, these topological charges are disclinations or rotational defects, and their topological charge or winding number, right, tells you about the director rotation as we move around the defect. Okay, so here's an example of a singularity in a director field. Okay, and then what you do is that you look at the director and you see that it rotates by 2 pi once you go around the defect by 2 pi. So this has a topological charge of +1. Okay, here's another singularity, right? Another topological defect, right? In this case, once you've gone around the defect by pi, the director has only rotated by pi halves. Then you complete the 2 pi rotation, and then you get an overall pi rotation of the director. So this is a 1/2 disclination. Okay, of course, the sign emphasizes that you can have negative disclinations, right? Here's an example of a -1/2. Still, you do have a pi rotation as you go about the defect by 2 pi. But now in this case, if I rotate around the defect counterclockwise, the director rotates clockwise. Okay, hence the minus. All right. So in the end, your director field on the surface must fulfill this theorem no matter what, right? And that's topology. Okay, so in the end, this theorem imposes what we may call a topological constraint on the director field. Okay, so let's see how this works, right? And this will connect with some of the earlier work into this topic, right? So think of a sphere, right? We've said already it has no handles. It has another characteristic of 2. And then you realize as a result of Poincaré-Hopf index theorem of why the sphere is so interesting, right? Is that no matter what you do, you must have defects. Since chi, it's equal to 2. So you need to have an index equal to 2. Okay? And in fact, what was predicted for the sphere, since this is only a topological constraint, so you just need to fulfill this, but you can have different types of defects with different types of topological charges that will comply with topology, right? What turned out to be the ground state, right, where you minimize energy, was predicted to have 4 1/2 disclinations, right, on the vertices of a tetrahedron. Okay, and a director field that's reminiscent of the baseball seam. Okay, so how did we tackle this problem, right? So again, we used microfluidics for this, right? And so here again, we have the co-flow that I've told you about. But now what you do is that you complete this device with a third capillary that's also cylindrical. Okay, that's facing the tip, yeah, right? The needle through which you're injecting the inner liquid. And then what you do is that you have an inner liquid, a co-flowing liquid, and now through the voids left between the circular and square cross-section of this other third capillary, right, you pump a third liquid that faces the co-flowing liquid. And then this orifice right here of this third capillary is the exit, is the only way out. So all the liquids have to exit through that orifice. So this third liquid that I've told you has to return backwards, right? And in doing that, focuses the co-flowing stream through the orifice, okay? And these, in some regimes, can result in the formation of double drops, okay? So here's an example, right? That's your inner liquid, right? This is our liquid crystal phase, right? The co-flowing liquid, and then this is the outer liquid, and you can see that in some regimes, you get these beautiful double drops, right? In our case, we're making a water drop in a liquid crystal drop, all inside water, okay? You can call this, of course, a liquid crystal shell, okay? And then what do you see? You look at it, you use cross-polarization. So again, I won't tell you about the details of the technique, but I can if you're interested at the end, or we can talk some other time, right? But once you look at these nematic shells, right? I mean, the defects located at the top, which is the thinnest region because you have a density difference between water and the liquid crystal. So the water drop floats, so it comes up a little bit. And you look at it and you have the defects at the top, right? And if you are familiar with polarized microscopy, well, you identify 4 defects, right? And these defects each has a charge of a half, okay? Now, of course, what was predicted was a tetrahedron, but then we're dealing with a shell, not with the nematic on the 2D sphere, right? If you thin the shell, which we do using osmosis, right? We add some salt in the inner water droplet, so you get diffusion of water in, you swell the inner water drop, you make the shell thinner, and eventually you have something that's reminiscent of a nematic on a sphere, and in that case, you do find the expected tetrahedral organization that was theoretically predicted, okay? But of course, when you do experiment, in many cases, right, you find other things that weren't predicted by theory, so we also found other defect structures, right, like this one at the bottom, right? So you here have 2 defects. You can see that they're different to the defects that we have looked at before, right? These are actually S+1 defects. So you get a different structure with 2 S+1 defects, but then you can have a hybrid one with 2 S+1 halves and an S+1. Now, the point is that no matter what, right, of course, you have to comply with Poincaré-Hopf. The index must be equal to the other characteristic of the sphere, which we know it's equal to 2, and there's no way out. That always has to be true. Now, the defect organization, location, type of defect structure, that's where the physics enters. Okay, so let's move on to the torus now. Okay, so an interesting parameter that I'll be referring to is the ratio between this length scale, the radius of the central circle, and the tube radius, right? So this kind of tells you about how slender your tori is, okay? So topologically, the torus has 1 handle and another characteristic of 0. Okay, so that tells you that no defects are necessarily required, okay? And in fact, in the first experiments that we did not look at a nematic on the surface of a torus, but rather we filled the torus with a nematic. So we had a solid torus of nematic liquid crystal, right? And here we didn't see defects on the surface, right? Consistent with Poincaré-Hopf, right? But we did see within the torus an interesting nematic organization that spontaneously broke reflection symmetry. Okay, so you became chiral and adopted inside the torus what's referred to as a double twisted organization. Okay, but now the key here is that even though no defects are needed, right, you can have, of course, an arbitrary number of positive and negative defects, right? I mean, the only constraint is that the index, the sum of the topological charges, has to be equal to 0, which is the other characteristic of the torus. And in fact, that was theoretically predicted for a nematic on a torus. Okay, so what was predicted by Nelson, Bowick, and Traversé, right, is that the ground state of this material for a sufficiently fat tori will have defects in the ground state, right? This will be there for energetic reasons. But not only that, the defects will actually not only appear, but they will couple with the underlying Gaussian curvature, right? And they will migrate positive defects to the outside where the Gaussian curvature is positive, and negative defects to the inside where the Gaussian curvature is negative. Okay, so the idea, if, for example, I look at the outside of the torus, right? So I'm considering now the half part of the torus with positive Gaussian curvature, and I'm going to plot the topological charge as a function of the integrated Gaussian curvature, and then I'm going to move azimuthally along phi hat. Okay, so what's going to happen is that eventually I cross a defect, and the topological charge jumps by a half, right? Across another defect, I get another jump, right? And I have 4 defects with a 1/2 topological charge each. Okay, now I told you that each of these 1/2 disclinations imply a pi rotation. So you have a net 4 pi rotation, right? And that's identically equal to the value of the integrated Gaussian curvature of the outside of the torus. So you can think of these charges as actually screening the underlying Gaussian curvature, okay? The other thing is that these jumps, and this is the purpose of this slide, is a highlight that, of course, topological charge is quantized. It comes in quanta of 1/2, okay? And then you can do a similar argument for the inside of the torus where the Gaussian curvature is negative, and when you end up having 4 negative 1/2 disclinations. Okay, so these theoretical expectations was our motivation to get into this. Okay, and this was actually why we got to make toroidal droplets in the first place. So we learned how to stabilize them in the way we found interest in fluid mechanics, as I've already told you, right? But in the end, we were pursuing this problem. Okay, and what we wanted is to address this coupling between topological charge and Gaussian curvature. Okay, but the way we ended up doing this is instead of using a conventional nematic liquid crystal, conventional mean in equilibrium, right? We used what's called an active nematic, okay? So it is out of equilibrium, and active here refers to the fact that there's energy input at the single particle level, locally, okay? You're locally bringing the system out of equilibrium everywhere, okay? And because of that, as we will see, there's a few interesting surprises. Okay, so how do we have a nematic on a toroidal surface, right? And of course, we had made spherical shells. So we thought, why not use a coaxial needle and make a toroidal shell? But then, of course, you realize that you have to close it. Right? You have to close your curved jet. And if you're using a coaxial needle to make a toroidal shell, then you're going to run into problems when you try and close it. So we ruled that out. But at the time we were thinking of this, right, there was this beautiful work in the lab of Zvonimir Dojic. At the time he was at Brandeis. Right, then he's now at Santa Barbara, and he developed a nematic that he called active nematic. Okay, and what we found appealing of this is that you had a nematic, right, and they actually had succeeded in depleting them to spherical surface. So we thought of using this type of nematic to deplete it onto a toroidal surface. Okay, so what is this active nematic? So the chemistry, it's impressively complicated for a simple-minded physicist, right? It has 4 major constituents. Right, so the building blocks are these rigid microtubules that are rod-like. Okay, they are bundled together by a depletant. Okay, that's a free polymer. Okay, so you get these microtubule bundles, and then the active part comes because you have these molecular motors that are able to bind on the microtubules, and they can walk on them and exert stresses on them, right? If they have the right directionality. Okay, and then these motors are driven by chemical energy. Right, so they're consuming that, and that is your local energy input. So in the end, the system as a whole, it's an active material, okay? And the dynamics of this active material at very high concentrations, if you think of it in bulk, is that you get this activity that's exerting these extensive stresses on the microtubules within the bundles, right? But then if you're really dense, you percolate through the system, so you can't keep sliding forever. So at some point, you do something else, so you buckle. Right, so you develop high curvature regions, right, because you just can't fit pretty much, okay, and then after buckling, you get fracture, and then these fragments recombine again, and this happens all over, as provided you have enough ATP and it lasts sufficiently long, okay. So this is how this looks, right? We image using confocals, and you can label the microtubules so that you can see them, okay, and that's how the system looks. You have these bundles, you can see these buckling instabilities, breakup, recombination, right? So it looks like a thermal system, but there's no temperature. Okay, so if you tune down the activity, nothing moves. Okay, so this is completely out of equilibrium, and it is driven by these molecular motors. That's the activity in the system. Now, what's interesting for us is that, of course, if you have a surface and you can get enough of these microtubule bundles onto the surface at sufficiently high density, you form something that begins to be reminiscent of a nematic liquid crystal, okay, where you can even identify some of the excitations in the director field, right? And these come in our system in the form of negative 1/2 and plus 1/2 disclinations. But then you're active, so of course you're gonna get some dynamics, right? And these buckling events and fracture events will happen within your active liquid crystal. So what we did is to use this material, we put it inside a torus, and we depleted it to the surface. And this is, again, one of the first experiments that work. Okay, so this is a C-scan. You can clearly see that most of the material is on the surface, but it forms an active nematic. Okay, and this is a reconstruction. Right, so we're imaging half of the toroid. Okay, in time we became better, right? And this is newer data, right, in which we have something that's a little bit closer to a torus. Okay, you can see the handle. Again, we're imaging the lower part. It's confocal. And it's active, right? So you can track it in time. The dynamics are sufficiently slow that confocal is fast enough to really track dynamics. Okay, so that's effectively the data, right? I mean, that's the key part, the key aspect of our work, right? Is collecting that data. And then the next step is what do you do with the data? And of course, our goal, as I've told you, was to correlate topological charge and Gaussian curvature to address this coupling that's expected, right? And this defect unbinding driven by curvature. Okay, so let me first tell you a little bit about how do we quantify the topological charge within our director field. Okay, and for this we talked to a mathematician, a colleague of mine back at Georgia Tech, right? And he mentioned that we should use this technique that's widely used in computer vision, right? It's called coherence enhanced diffusion filtering. Okay, so we paid attention to what he said, we studied the papers, and we used them, right? So what is coherence enhanced filtering, right? So very briefly, right? Imagine you have an image, right? It's pixelated. So let me consider a pixel. In that pixel, you have a grayscale intensity that I'm gonna call I. And then you can, at each pixel, construct the gradient in intensity, okay? And then you can take that gradient in intensity, you can think of it as a column vector, and then you can multiply by the transpose to generate what's called the structure tensor, okay? Or if you want to think of it in terms of matrices, a 2x2 matrix, okay? And then what you do is that you diagonalize this tensor, and you're interested in the eigenvector associated with the smallest eigenvalue, okay? And that's going to give you the direction along which the intensity changes the least, okay? Which it's in the computer vision literature, it's called the coherence direction. If we were to think in terms of liquid crystals, right, that's what we would call the local director or the molecular director, okay? And then you can already plot this eigenvector by assigning a grayscale intensity to a given direction, okay? So here's an example. You have a fingerprint, okay? You do what I've just told you, and you can say that, okay, if the coherence direction or the molecular director is horizontal, I'm gonna put that black. If it's vertical, I'm gonna draw it white, okay? And you can see that whenever you're most horizontal, you're the blackest, and whenever you're most vertical, you'll be the whitest, okay? So that's that. And we can do that with our tori, okay? So this is an inner part of a torus, this is the outer part. This is just a projection onto the plane without anything fancy, right? And this is the orientation map of this molecular director, okay? But then once you have the molecular director, you can construct the order parameter of the nematic phase, which is the Q tensor. So you basically average, right, around, and you get this Q tensor. You get it everywhere, right? And then diagonalizing that new tensor gives you the scalar order parameter and the associated eigenvector, which is the director. Okay, and that's how this works. So from the molecular director, we can look around, average, and construct the Q tensor, and from there we can get maps of the scalar order parameter and the associated director field. And then what you do is that you look for regions of low values of S. These are candidates for defects, right? Low S, right? Low order, nematic order. And then what you do is that you put yourself in such a region, you look around, and you see if you're a defect, right? Because there's a net director rotation as you move around by 2 pi. And then you can also quantify the topological charge, okay? And that you can do that, and this will be the instance for the snapshots that I've just shown you. But then you can do that in time, okay? So you can identify, characterize, and track defects, right? Here, the +1/2 are the triangles, the stars are the -1/2. Okay, great. So that's how we quantify topological charge. Now, what about Gaussian curvature? Right. So again, this nematic, this active nematic, lies in a toroid. So you need to quantify the local geometry. We're interested in the Gaussian curvature at each point. And of course, you may think, okay, so there's differential geometry that you can use, and of course, that's true, right? So K is nothing but the determinant of this matrix, the Weingarten matrix, this shape operator, as you may want to call it. I mean, aside of the details that I'm not going to get into, the shape operator is related with doing derivatives of the normal, right? U and V are tangent vectors at each point, right? But the key point is that, yeah, this is all beautiful, of course, but it involves doing derivatives, and we have numeric discrete data, which is also noisy. So you can't really do derivatives. Okay, so you can't just use this because we just can't do derivatives. Okay, so this is what we ended up doing, right? So again, we talked to our colleague, the mathematician, and he told us you have to study these papers. And since the first part worked so beautifully, we did exactly what he told us. And in the end, he was right? So this works amazingly well. The notion of what you end up doing, or we ended up doing, is that if you take this Weingarten matrix that I've told you, the action over a displacement field at a given point on the tangent plane gives the associated change in the normal. Okay, and then the interesting thing is that, of course, you can triangulate your surface, you can measure changes in normal associated with given displacement vectors, right? And you can then do a least square fits pretty much, right? It's a robust methodology, but in the end, that's what you're doing with the components of the Weingarten matrix left as unknown. Once you obtain the components from the fit, right, you can take the determinant and you get the Gaussian curvature. And here's an example. This is a section of one of these toroids, right? And this is the underlying Gaussian curvature map, okay? So you see that at the bottom, you have a line of zero Gaussian curvature, then the outside it has positive Gaussian curvature, the inside has negative Gaussian curvature. So again, this works beautifully. So once we have these two pieces of information, we can then correlate them, okay? And let me remind you here that what we have, it's a global constraint, a topological constraint on the full torus, right? Remember, the index of the field has to be equal to the Euler characteristic of the torus, which is 0. Okay? That's Poincaré-Hopf applied to the torus, okay? So that applies to the whole torus. However, what we're going to be doing is looking at patches within the torus, okay? But I'm going to start looking at a patch such that the integrated Gaussian curvature is equal to 0. Okay, so that's what I'm going to do. And then what we're going to do also is that within that patch, because you have lots of defects that are created, they're annihilated, right? They move in and out of this patch, right? I'm going to calculate the time average of the topological charge, of the net topological charge inside that patch. Okay, so here's an example of a relatively fat torus. Again, that's the inside, this is the outside, right? This is what you're seeing is the active nematic, the projection onto the plane. And here's a patch with no net integrated Gaussian curvature. And then what we do is that we measure, we identify our positive and negative defects, they change over time. We can calculate a mean topological charge, right? Net and mean topological charge, which turns out to be 0. Now here's another toroid, this one a little bit more slender, same exercise, right? Here's your patch, no net integrated Gaussian curvature. You look at the mean index of the field, right? The net topological charge, average on time, and again, you get 0. Here's an even thinner toroid, same thing, a patch, no integrated Gaussian curvature, mean index, again, 0. So that's pretty cool, right? Because we're not looking at the whole torus, we're just looking at a part of it, right? With no integrated Gaussian curvature, but as soon as you have no integrated Gaussian curvature, that seems to be representative of the whole, right? So you get that in the end, the index, it's also equal to 0. It didn't need to be the case, right? Topology applies to the whole torus, but this is what we find. Okay, but then of course, very naturally, you can say, well, you can choose a patch with a net integrated Gaussian curvature that's negative, right? You do the same, you measure the index of the field, and you get a negative value. You can also choose a patch with a net positive integrated Gaussian curvature. You measure the mean index, averaging time, and you get a positive value. You can put all the data together, right? That's the mean topological charge as a function of the integrated Gaussian curvature. And the first thing that you realize, this is for different tori, different aspect ratios, right? Different geometries, right? Is that, as I've already mentioned, the data goes through 0, 0, right? So, and that's true even if we're not looking at the whole torus. So that we were expecting that to be true for the full torus, but this is also true, right? In this active nematic instance. Okay, so choosing a patch with no integrated Gaussian curvature, as I've already told you, seems to be representative of the full torus. Okay, but the other interesting thing is that the data clearly shows this coupling with curvature, right? So if I look at regions of positive integrated Gaussian curvature in the outside, you got an index which is positive, right? So on average, more positive defects will be located in the outside, right? And then the same thing happens for the negative regions, right? So you get negative defects located in regions of negative Gaussian curvature. Yet, of course, it's an active system. So defects are created and annihilated. They move and explore the available space, right? And in a sense, this brings about, if you were to think or connect with equilibrium physics, right? It brings a little bit of a flavor of a high temperature limit, right? In fact, S, right, this topological charge becomes a continuous variable, right? In this active limit, right? It is no longer discrete as we were expecting. It's like in the quantum limit, everything is quantized. You crank up temperature and things become continuous. So this has a little bit of that flavor. So in the end, what you can say is that we have seen experimentally this defect unbinding due to curvature, right? But we're seeing these on average. Okay. All right. Now you can of course look a little bit deeper into this and not only look at this net topological charge, right? The difference between the positive and negative net charge, right? But you can then look at how the defects distribute within the torus, okay? And here, if we were to go back again for equilibrium expectations, what we would find is that, again, for energetic reasons, you can get pairs that are created. This happens in regions of zero Gaussian curvature, and then you get this coupling with the underlying Gaussian curvature, such that you will only find positive defects in the outside and negative defects in the inside. Okay, so if we go to the continuum limit, right, what we were expecting is something like this, right? In this case, now we're plotting at the densities of positive and negative defects as a function of the mean Gaussian curvature, right, and of a given patch, right? And what you find is that you expect more defects in regions of positive Gaussian curvature in the outside relative to regions of negative Gaussian curvature, and the opposite for negative defects, right? So based on equilibrium expectations, right, you would expect the density of negative defects to be larger in the inside of the torus and smaller in the outside of the torus. But when you look at the experiment, you find something completely different, okay? What you find is that both positive and negative defects are larger in the inside of the torus, okay? Of course, the difference is such that you get this beautiful connection with the equilibrium instance, right, in which you do see these curvature-induced defect binding, this overall coupling with the underlying Gaussian curvature, but the defect distributions are very different from what we were expecting based on equilibrium expectations. Okay. In addition, we can measure the creation and annihilation rates, right? So again, positive and negative defects can annihilate. You may get creation in a different region, right? And then we can quantify that in our data. And what we find is that the two rates more or less match, and the rates are larger, or seem to be slightly larger in the inside, right, relative to the outside of the torus. Okay, so here's what we think is happening, right? So here's our conjecture of these results, right? Is that what we conjecture is that the fact that the densities of positive and negative defects are larger in the inside have to do with the fact that there are larger director distortions in those regions, and that those distortions are driven by the activity. Okay, so if that was to be true, right, you have larger end distortions in the inside, so you're going to imbalance the creation rate towards the inside. So you're going to have a larger creation rate of defects in the inside of the torus relative to the outside. Okay, and then of course you have this coupling with Gaussian curvature. So in the end, the positive defects will want to move outside, the inside, the negative ones will want to remain in the inside. But then because you have a lot of defects, right, the mean free path of the defects are relatively small, and then you can't have complete segregation. Okay, so in the end, right, and what this amounts to is having both types of defects at higher densities in the inside of the torus in regions of negative Gaussian curvature. Okay, so here's where the numerics and simulation work by Dan and Luca was instrumental to really address our conjecture from the experiment, right? So they did the beautiful hydrodynamic calculations, right? So they wrote down basically Navier-Stokes, right, for a nematic liquid crystal. So you get these additional viscosity terms and this coupling between director field and flow, right? right? And they wrote these equations on the surface of a torus, including the effects of activity, right, in the stress tensor, okay? And then what they found is that they calculated the shear rate, okay? And let's forget about the different lines. I mean, they all show the same. These are just different values of activity, right? This parameter that's bringing the system out of equilibrium. But in the end, what they find is that this shear rate seems to always be larger in the inside of the torus, right, compared to the outside. So it is larger in regions of negative Gaussian curvature, okay? And then as a result of this larger shear rate, right, you're going to imbalance creation towards the inside. So that's always going to be larger in the inside of the torus compared to the outside. The annihilation rate matches, right? And then that results in a defect distribution, right? Positive and negative defect distributions that are consistent with the experimental findings. They also looked at a particle-based model, right? That where you're thinking of the topological charges on the plane, they interact, right, in a way that's reminiscent of how charges interact. So you can refer to what we refer to as this particle-based model as a Coulomb gas model, right? So the idea is that you have these, you're forgetting about the director field of the active nematic, and you're just focusing on the defects, right? So the defects are your particles, right? They have a self-propulsion due to the activity, right? And then they interact within themselves and also with the underlying Gaussian curvature, okay? And here you can tune different parameters independently, so it's a nice way to test the influence of the different aspects, right, in the problem, okay? And the way we were able to capture the results of the hydrodynamics and also those in experiments is by incorporating a little bit of a higher creation rate in regions of negative K, okay? So the idea here is that when two defects get sufficiently close, they annihilate, and then you create a pair. But that pair is not randomly created anywhere on the torus, but there's a little bit of a bias towards the inside, okay? And so that's some snapshots, right? You start with the positive defects in the outside, in the inside, they move around, you get creation and annihilation events, right? And on balance, the creation rate towards the inside, and then what you find is that the annihilation rate matches the creation rate, right, that you're imposing, and then that the resultant arrangement of defects, right, the defect densities of positive and negative defects beautifully match what we see in the experiments. Okay, so this somehow confirms our interpretation. Okay, so I still want to tell you a little bit more, but here's a little bit of a final remark, right, to some of this work, that soft matter, it's great, right, for tackling problems where you have topological and geometrical issues, right? And precisely that's the case because you're soft, right? In that case, the material becomes sensitive to these aspects, right? If you're rigid or very rigid, at some point, that's all that matters, right? And of course, you can go to reciprocal space and do or find interesting topological instances, right? But here you have these in action in real space, right? And then we've become kind of obsessed with toroids in my lab, right? So we use toroids for a lot of things, right? So we tackle different type of physics, right, using toroids. And what I've told you a little bit about, it's about some of our work on active nematic tori, right? Having the active nematic on the surface of a torus, okay? All right, so let me end by briefly addressing some of the more recent work, okay? And that this, in a sense, it focuses on the defects per se, right? So not so much on the active nematic, but then you look at the defects, and those are your kind of particles, and they're active particles, right? Because they're able to move due to activity, okay? And in fact, if you take these defects, you can associate a directionality to them, okay? Here's a +1/2, and it's a polar defect with a directionality p, right? The -1/2 it has a 3-fold or 6-fold symmetry, right? And you can associate some directionality to it also, okay? And then what we've been wondering is on whether the defects themselves, right, as the degrees of freedom, develop some form of order, right? And in particular, we've been focusing whether the defects, because they have a directionality associated to them, whether they develop orientational order, okay? So here's what we do. So here's a snapshot. So we do exactly what I've told you before. We identify the defects. We have a director field. We can assign a topological charge. But then on top of that, we can now also associate a directionality. Okay. And then what we're looking is on whether there's some sort of orientational order among these defects, which, as I'm telling you, you can associate a directionality to them. Okay, and what we find is that there's no sign of long-range orientational order. Okay, so we have no signatures of this, and this is at odds with some of the earlier results that have been published. Okay, so we have no trace of long-range orientational order. However, we do find interesting orientational correlations, right? So here's a correlation function associated to the orientations of two defects, right? And we're plotting this as a function of the distance between defects, right? I mean, here we're normalizing with the mean defect separation, right? Which depends on the defect density. And what we find is that, of course, at large distances, that's effectively zero. There's no orientational correlation. But then at sufficiently small distances, when you become comparable to the defect spacing, you do develop an anti-correlation, right? So defects, I'm looking at the +1/2 defects only, anti-align, right? And then at even shorter distances, right, they tend to align. So this anti-alignment is sort of the natural thing if you think of +1/2 defects and you associate a directionality to them, right? So that's the natural way +1/2 defects can get together, right? Or closer, not together, but closer, right? At sufficiently small distances, right? So these accounts for this anti-correlation. But then, of course, how would they align if the distance is even smaller? And of course, this happens if there's a -1/2 in the vicinity, right? So they can actually align, right, in their orientations if there's a -1/2 that is somewhere nearby. And that accounts for this sort of correlation at short distances. And then similar results are found in the numerics, right, using these hydrodynamics that I've briefly referred to before. So that's great. Okay, so what we're now looking at, it's right, so what I've told you happens or is seen in flat space. What we're now doing is looking at these on curved space, right? So we're trying to address whether some form of order between the defects arises, right, as a result also, or mediated via the coupling with the underlying Gaussian curvature. So in the end, this amounts to thinking of the defects as the active particles and trying to say something, right, about the collection of in this case, defects, right, again, as active particles. And with this, I thank you very much for your attention.
Thank you very much, Alberto, for such a wonderful talk. And now we have time for questions.
Let me see if I can see people.
You can use the raise hand button or just unmute yourself. Juan, go ahead.
I don't hear you. I still don't hear you.
So can you hear me now?
Yes.
Okay.
Perfect.
So, sorry about that. Nice talk. I was wondering when you presented the thin cell experiment with the nematic in the core, at the core, that you observed these charges assuming +2, right?
Yes.
But
you're talking about the spheres.
The spheres, yeah. So, but you experimentally see different arrangements that you predict using theory, right? Those arrangements are stable or are dynamic, so they can switch between different arrangements.
Yeah, it's a good point. So they don't switch.
Once they reach that arrangements, they stay there forever.
Yes, I mean, of course, you have thermal
fluctuations,
thermal jiggling, right, of the defects, but in the end, there's no transition between defect structures, and the reason is that there's a huge energy barrier between them.
Okay.
So what this tells you right away is that there are many metastable states or some metastable states. Okay,
and
so for example,
no, continue. Sorry.
Yeah, so in this case, for example, the lowest free energy state will be the one with 4 1/2s. But if when you create the shells, you for some reason have 3 defects or 2 defects, right, with different charges, you are able to have them there because there's a huge barrier between going from these defect structures to the 4 1/2 defect structures. And we have
And
no
what-
control over that. At least we didn't. Now maybe there are methodologies that people could have developed that at the time we didn't, right? We just
Yeah.
made the double emulsion, and when we
see
looked,
what happens.
exactly.
And what will happen if you make now in this system an active nematic crystal? Because
So
now
what-
I guess that you can cross those barriers and observe this.
Exactly. So that's interesting too. So let me tell you. So this is the baseball, right, with the tetrahedra is expected for a nematic on the sphere when the elastic constants, right, for bend and splay are comparable. Okay. Now, if you make bend or splay very different in terms of the energy cost, so the Frank constants, you make them very different, then the ground state is no longer a tetrahedra, but the defects migrate to a great circle.
Oh.
Okay. So what seems to happen in the active case, which is kind of cool, is that the +1/2 defects, they move around due to activity, and they seem to be oscillating between the great circle and the tetrahedra.
That's cool.
Which is what you would expect from equilibrium instances, right? In the case of comparable Frank constants or very different values of splay and bend elastic constants. But yeah, in the active case, yeah, they move, they expand phase space, right? And whenever you have only 4, because that's also an issue, is that in some of these active spheres, you may have many defects when the sphere is large enough. So you have to have a small enough sphere in order to only have the 4 disclinations. And then you can track their dynamics and you see what I've just told you.
And if I may, one very last question.
Yeah, that's great.
When you presented the trajectories on the toroids of the defects, which was the first ingredient of your analysis?
Yes.
It looks like, just with the short view that I had, that they have different velocities depending on the defect.
That's indeed true. So I'll tell you why. I haven't told you about it on purpose. Okay. So of the 2 defects, right, the 1/2 and the -1/2, the only one that self-propels is the +1/2. Because of the symmetry. Because you have you become polar, and then that defect is the only one that self-propels due to activity. The -1/2, because of the 3-fold symmetry or 6-fold symmetry, has no net propulsion. So in the end, the triangles are the ones that you see moving more, right? Those are the ones with a self-propulsion speed. The -1/2s only move due to their interaction with the other ones and due to the interaction with Gaussian curvature. So yeah, you're totally right. It's a very good eye. I didn't mention any of these on purpose because it's a little bit of a detail, but yeah, it's an important detail. So, and that's also why, yeah, the high temperature limit, it's a way that you may think of some of what we're doing, but it's not quite correct, right? Because only the +1/2s are the ones that are truly active, right?
Okay,
Those are the ones with a self-propulsion speed.
And have to measure or have a distribution of velocities they have an average velocity, and it changes with the curvature, or
we haven't detected much change, right? For the time span that they move, they seem to be moving with a constant speed, right? And so that seems to dominate over other effects, right? And
looks a correct approximation. So the simulations, I guess that you put a constant velocity and you recover the behavior. So
yes. So in the simulation, you put a constant velocity V0, which you can connect with this activity coefficient that you write down when you think of the continuum model, right? When you do the hydrodynamics, right? And so that coefficient determines both the speed of the 1/2 defects and also the number of defects. So increasing the activity causes more defect pairs to appear, and at the same time, the +1/2 defects move faster, and there's a little bit of a coupling between them.
Yes.
Okay, but in the end, yes, in the particle-based model, you can consider that. So when we change V0, the velocity of the +1/2 defects, we also change accordingly the total number of defects, so that we're in agreement with the aerodynamics. And the key to capture the experiments is to unbalance in the Coulomb gas model the creation rate. And that told us that we were right, that in the end, you really, everything gets biased towards the inside of the torus, towards the regions of negative Gaussian curvature.
Thank you. Really cool.
Thank you. Any other questions for Alberto? I may ask one final question. In the nematic shells also, have you changed shell thickness to see if if you favor the ground state defects or if the others appear more as a function
Yes.
of shell thickness or something like that?
We have. Yeah, we
and
have.
what happens?
So typically, when you have an S+1, so remember that you're bounding the nematic between two spheres. So on each of the spheres, you need to comply with Poincaré-Hopf. Okay, so here it looks like you just have one S+1 and another S+1, but in reality, you have two pairs of Booleans, one on the top sphere and one on the lower sphere. It's just that they're looking from above and they're at the top of it, so they look one below the other one. So if you make the shells thicker, this is the structure that prevails. Okay, and if you're sufficiently thin, then you're biased towards the 4 1/2. And then the hybrid happens in between.
Okay, yeah.
Then, of course, there's interesting defect reorganizations as you change shell thickness, right? Which we did by using osmosis, right? So using osmosis, we can sort of quasi-statically change the thickness and you can track where the defects are. And you can see, again, there's no transitions between defect structures, but the locations of the defects, right, do change. And for example, here, you find a very nice, reminiscent of a first order phase transition, confinement, deconfinement transition. So here you're confined to the thinnest part, but if you make the shell thicker, at some point abruptly, you get another pair at the bottom along the diameter. So yeah, we've played a lot with that, and it's quite interesting.
I see. Great, thank you.
You're welcome.
Okay, if there are no more questions for Alberto, we close the session here, but let me mention that next Thursday, we will be having our next seminar, which will be given by Lucas Lamata from University of Sevilla, and who will be talking about quantum simulations of condensed matter systems with quantum technologies. So please join us again next week for that seminar. And with this, I want to say thank you again, Alberto, for the great
Thank you,
talk.
my pleasure. Yeah, great.
Bye, and see you all next week.